Welcome back. Now we will see how a numerical overcurrent relay will be implemented. As already seen in the previous lecture, that we need to consider 5 to 6 things when we are implementing a numerical overcurrent relay. Now, let's see how the algorithm is to be implemented. Numerical overcurrent protection is a straightforward application for numerical. So, when I say that numerical overcurrent protection is to be implemented, we need to write an algorithm about how it must be implemented. As already seen in the very first class of unit number 4, that it's all about the programmer writing a useful program and then implementing it with the help of any software or a programming language. So, in this lecture, we'll try to develop a particular algorithm for implementing a numerical overcurrent. So, what are the steps which will be involved? The very first step in implementing a numerical overcurrent relay is we must know about the settings which are to be implemented. So, the type of characteristics which are to be implemented, the pickup value, the time multiplier setting, because time multiplier setting will be applicable only in case of inverse relays, and definitely you won't be having any time multiplier setting. So, you must know about the characteristics of relay, and then you must check what is the time multiplier setting. If it is not an inverse relay, then you will be having just only time delay. In case of definite time overcurrent relay, you will be having a time delay. In case of inverse, you will be having time multiplier setting. So, what are the things which you must know before you start implementing? The type of characteristics. If it is inverse characteristics, you must know time multiplier setting. If it is definite time overcurrent relay, you must know time delay. And also per unit, pickup value. These you must read before you start implementing. And next, once you get these things, once you do have this basic values of time delay or time setting or pickup value, then you must be able to retract the data from your main signal. So let us suppose if my main signal I circuit. First of all, this circuit, which let us suppose if I am taking a power system, the data is obtained here, and this may consist of some harmonics. So the next step is nothing but you should extract fundamental components, and then you need to compare it with your pickup value. So you extract your fundamental component. I call it as an RMS value. So if there is a fault, you will first record the data and then you extract the fundamental component and you determine what is the RMS value of that one. And next, this RMS value, as already I told in unit number 2 and also in unit number 4, how to obtain extract fundamental component. You can use it Walsh techniques or Fourier techniques or least error square techniques. We have seen so many techniques. With any of these techniques, you can determine what is the fundamental component. Once you get this fundamental component, you compare this one with your per unit value. Pickup value. Okay. You compare this one with your pickup value. If it is greater than your pickup value, then you need to trip your circuit. If it is not greater than, then you remain silent. So this is the simple thing which you are supposed to implement. Additionally, there might be few other steps also. So once you have this plug setting multiplier value, then if your RMS is greater than or equal to PU, if this condition is satisfied, then immediately you will check for PSM value. So it will compute your time multiplier, or it will look up for any time delay setting which is available. So once it is done, immediately it will check for time setting or time delay. Relay satisfied. Now, when to give the signal? Should I wait for some time, or should I wait some more time, or should I give it instantaneously? Once the condition is satisfied, it will check for time setting. Based upon this, it will give a signal. So the algorithm will then cause the relay to go into a wait state till your time condition is met. Your operating time is being met. Once the time delay is done, let us suppose if the condition is satisfied, then you need to wait for 3 seconds. Maybe it's a definite time overcurrent relay. So you need to wait for 3 seconds once your condition is checked. So at the end of this time delay, the relay will once again evaluate the RMS value. Still after 3 seconds, still if it is greater than your IRMS value, if it is still greater than your pickup value, after 3 seconds also, now the relay will issue a trip output. If not, it will automatically release the things. It won't release any trip signal. After 3 seconds, if it is still okay, then it will issue a trip output. Okay. Once it issues a trip output, then it will be suitably processed to make it compatible with the trip card. So this is the implementation now. We need to develop a flowchart or a pseudo code for this thing. So I'll start. This is a flowchart. This is your start. So first of all, what I must read? The type of characteristics. So what type of characteristics? Whether it's a definite time or IDM2 or inverse or extreme reverse. Apart from this, what I must read? Plug setting. And if it is a direct definite time, I need to go with time setting. If it is an inverse thing, I should go with multiplier setting. Right? This is all about reading itself. And then additionally, I should go with reading of samples, whatever the samples which I do have. Once I read the samples, once I do have all the settings, so immediately with the help of the samples, what I will be doing, I'll be applying some sort of Fourier techniques. You can go with full scale window or half scale window or whatever discrete Fourier transforms. What you will be doing, you will determine the RMS value. So find the RMS value. If your RMS value is greater than your pickup value, yes, then you will move on to the next case. If it is no, you wait for some other time, get your another samples, again check. So if it is greater than your pickup value, the next immediately what you will be doing, you will look up time delay. You will wait for this time. After this time, again you read the samples, find the RMS value, again check if it is still greater than your pickup. If it is still greater than, then you issue the trip output and it will stop your program. If it is not greater than, again you will go back to the samples. Understood now how to develop a flowchart, how to implement this overcurrent relay algorithm. Understood. So now this is the way how we develop algorithm. So if you are a programmer, then automatically you will develop a code for this thing. Understood. Now we will see so many manufacturers are now manufacturing this overcurrent relays. One such company is Siemens. Normally in your IEEE standards, overcurrent relays are represented by the number 50. Overcurrent relays or earth fault relays, they will be represented by 50 or 51. It is either definite time or inverse time. So whenever you are dealing with overcurrent relays, try to remember this number 50 or 51, depending upon the characteristics of the overcurrent relays. There are so many companies. All India is there, Siemens is there. All these companies, they develop this, they manufacture this numerical overcurrent relays. So now we will have a look at an overcurrent relay which is developed by Siemens. This has been taken from the internet. The data has been taken from the internet. You can find it over the internet. So as you all know that overcurrent relays or earth fault relays, they are the basic protection relays. They protect your transformers or other circuits against overcurrents or earth faults. When excessive current flows in the circuit, these overcurrent relays, they will issue the trip signal and the circuit breaker opens the circuit. So now I'll show you. This is developed by Siemens. This is an overcurrent relay. If you carefully see, this is the display unit where you will find the display, and these are the LEDs which will give you signals. Depending upon this LEDs, glowing of these LEDs, then automatically you will try to analyze what happened in the circuit. Okay. Now I'll show you what actually these LEDs represent. Okay. And these are the different settings which you do have on the panel. Okay. See what actually this device can do. The Siemens device can do. The first thing is phase overcurrent protection, which means that whether it is definite time or time overcurrent based upon the IEC standards, that it can do. And this N indicates it is an earth overcurrent protection also, and it can also offer your ground fault protection also, and also strip circuit supervision, and also if there is any breaker failure also. These functions they will be provided by the relay which I have shown. Okay, these were mentioned in the manufacturing sheet of that particular relay, so I don't have any information about how these will be implemented, but these functions can be provided by that Siemens relay. See how many functions it is providing. In case of electromechanical things, we should have used separate relays for each of these things. But here, it is capable of protecting the circuit against phase overcurrents, earth currents, ground faults, trip circuits, and also breaker failure also. All in one single circuit. And there are 7 LEDs I have already shown you. So what does that indicate? The first LED is, I will show you. See, this is device OK. This is gen trip. This is TCH. This is trip. This is E by F trip. This is earth failure. This is interlock OK. So what actually these stand for? The first thing is device OK LED, which means that if the light is lit, which means that the relay is operational in protecting the circuit safely. The second one was general trip. If it is lit, then it indicates that when any protection tripping occurs, it causes breaker trips. And the third one is trip circuit healthy. It indicates there is no problem in the trip circuits. See, the next thing is overcurrent. It indicates that any fault causes overcurrent in the phase element of the relay that exceeds a setting value. Similarly, earth fault. It indicates for any fault which causes overcurrent in the earth elements. And breaker failure. If after programmable time delay, if the circuit breaker has not opened and the relay's fault is still sustaining, then it will indicate that there is a breaker failure. And finally, interlock. This indicates that when certain conditions are satisfied, for example, these things, breaker in service, bus voltage healthy, if these things are satisfied, then this LED will be lit. Now, in the previous case, I'll show you that see 1, 3, and 7. These are lit. What does this indicate? Which means that the device is okay, and the trip circuit is healthy, and the interlock is also okay. So which means that these 3 are basic LEDs which will be lit all the time. And the remaining things, if the 4th button is lit, then it means that overcurrent is happening. And if the 5th one is lit, it indicates that there is an earth fault. And 6th one, if it indicates, then there is a breaker failure. Understood? So based upon these things, we can identify what is happening in your circuits. Okay. So on the whole, I hope that now you have understood how these numerical overcurrent relays are implemented. It's all about, they use very advanced numerical relay devices. So what all you need is nothing but you should develop an algorithm. And if you are a good programmer, then automatically you can write that code. Okay. You must carefully consider the pickup current, time delay, curve characteristics, ground fault protection, communication monitoring, coordination with other protection devices. All these things you must be careful. So based upon that, you will be developing the algorithm and then you will implement the code. So you can consult with engineers, electrical engineers. There are so many guidelines which are available. The IEEE codes are there, IEC codes are there. You follow those codes when you are implementing this overcurrent relay. Okay. Overcurrent relay protection, numerical overcurrent relay protection is important for transformers to protect it against incipient faults and also internal faults. Okay. So that's it from my side. In the class, we will discuss more about these overcurrent relays, and in the next lecture, we will discuss about differential protection, numerical differential protection, which can be implemented for the transformers. Okay, that's it from my side. Hope you are now able to describe the numerical overcurrent protection, what are the things which you are supposed to consider, and how to write in pseudocode or a flowchart, and how to implement it. Okay, thank you. We'll meet again in the next lecture on numerical differential protection on transformers.